Okay, hello everybody. Welcome to this third edition of the MICCAI Special Interest Group for Challenges webinar series. And this time it will be all about metrics. So Lena, would you like to make an introduction of the group?
Sure, yeah. Welcome also on behalf of the entire Special Interest Group on Challenges. Today is a special day for us because we're actually presenting some of the Special Interest Group's work. And this work is, well, rooted in the fact that we think that the way we measure progress and how we decide on the clinical suitability of a method is all based on the validation metrics that we use. And they should, from our perspective, get much more attention than they actually get. And this is why the Special Interest Group, in collaboration with Helmholtz Imaging and also the MONAI benchmarking group, initiated this Metrics Reloaded initiative. More than 70 researchers have actually spent more than 2.5 years revisiting the important topic of metrics. And with this, I would like to hand over to our webinar chairs, PK and Camilla.
Yes, thank you so much for the introduction. So I will also give just a brief introduction on the student board. So I am a member of the MICCAI student board, and basically our goal is to encourage the involvement of students in the community. So we organize networking events during the conference, hold quarterly webinars, hold the educational initiative. And this webinar, as well as the other webinars of this series, you can find in our YouTube channel, which is here in the MICCAI Educational Initiative. So if you go there, you will be able to see the past recordings. We also have a Slack workspace in case you would like to join, and this is our Twitter. Okay, so with that, I would like to introduce our first speaker of the day, Paul Jäger. So Paul is a principal investigator at the Interactive Machine Learning Group at the German Cancer Research Center and Helmholtz Imaging. His research focuses on image analysis algorithms with a particular focus on human interaction. So thank you so much, Paul, for joining us, and the floor is yours.
Okay, I saw this talk that we have is actually joint talk with Annika. So maybe you also want to already introduce Annika.
Oh, we can wait for when it's Annika's turn.
So we're actually both talking at the same time.
Oh, you want to talk together? Okay, got you, got you.
Yes.
All right, I thought actually you separate.
No worries.
Problem. Yeah, so our second speaker, joint speaker together with Paul is Annika Rick, who joined the Division of Intelligent Medical Systems at the German Cancer Research Center to adapt mathematical concepts to societally relevant topics, such as scientific benchmarking and validation. So she has published disruptive findings on biomedical image analysis challenges in high-impact journals, such as Nature Communications. She is a founding member of the initiative of biomedical image analysis challenges, acronym BIAS, aiming for bringing biomedical image analysis challenges to the next level of quality. She serves as the secretary of a MICCAI Special Interest Group on biomedical challenges, this is a SIG group, and as the active member and task force lead of a MONAI working group on evaluation, reproducibility, and benchmarking. Thank you. Let's welcome our speaker, Annika.
Exactly, and one more comment. So you can see there is this Q&A box, so please post your questions there and we will address them later.
All right, let me quickly share the screen so that we can get started. All right. Or do you want to go ahead?
Yes, so thank you so much for having us. Thanks, Camilla, PK, and Lena for giving us the opportunity to speak here. So Annika and I are going to talk about Metrics Reloaded, so our framework for recommending image analysis validation metrics. So Annika, let's just start with a simple example. Let's say I have a problem where I want to classify some biomedical images and I'm looking for a metric to validate my results. So according to this study from 2018, where 100 international public competitions about biomedical image classification were analyzed, accuracy is by far the most used metric. So why don't I just then, let's say, use accuracy for my problem? I mean, if everyone's using it, it cannot be that wrong, right?
Actually, this depends on the question, and it can be very wrong. So it's a very popular metric and an easy to interpret metric. However, it also comes with some very popular flaws, and so popular that there are even memes about it. So let me explain to you why it's actually a big problem to use accuracy in imbalanced class distribution settings. Say we have a very simple problem. We want to classify patients into having a disease and being healthy. And on the left-hand side, so you see our data set for which we achieve an accuracy of 97% with our algorithm. Of course, this is a great score, but we should be careful with directly publishing in the next journal, because as you see, this data set is very imbalanced. So the problem that we were talking about earlier. So we have nearly only sick patients and only 3 healthy patients. And if we have a closer look to what our prediction is actually doing, it's just a very naive classifier, just always says that someone has the disease. So this accuracy value is actually giving us a very misleading score, saying that our prediction is nearly perfect.
Okay, I see. So, but then maybe to circumvent this pitfall in high imbalanced settings, I should use balanced accuracy instead, right? Because with balanced accuracy, it looks at the 2 classes individually and then just averages their sensitivities. And so it's not prone to these pitfalls with high imbalance settings. And we can also see here that for this example, we get a balanced accuracy of 50%, which is rightly indicating that it's a useless or naive system.
Well, in this example, it would be true that balanced accuracy would definitely be the better choice, but this metric also has its own limitations. So let's have a look at a different kind of imbalanced settings. So here you see a confusion matrix in which we have many, many negative samples. And if you look at those values, we see that we have nearly 5,000 false positives, which is an extremely high number. And just think of a real world scenario like screening or something. If you have 5,000 false positives, this could be very disastrous. But no matter of this problem, accuracy and also balanced accuracy will give us very high values, indicating that this prediction is actually very good. The problem is that the balanced accuracy is not having a look at the predictive values. And they are actually important in this setting. And if we would compute a metric like the positive predictive value, was actually looking at this, we would see that this value is 0. So indicating that this classifier is not doing the right thing.
Okay, I see. So you're right. So predictive values are also very important features of, let's say, diagnostic tests, and they're not accounted for here. So then I might use the Matthews correlation coefficient, right? The MCC, because the MCC takes into account all 4 basic rates of the confusion matrix. So the 2 individual sensitivities here, and also the predictive values, the positive and the negative ones. So you see that you only get a high score for MCC if all of these 4 characteristics are actually ensured or give a high score. So that would be an option here, no? Then I'm kind of done with my metric selection.
Again, I have to say no, because so MCC is working for the 2 examples that we showed earlier, but it again has some own specific limitations. One of them, and probably the most prominent one, is the prevalence dependency. So we want to compare our methods to different data sets, but they have a different prevalence, then we cannot use MCC to compare against across those data sets, because the prevalence will also influence the metric score. Also, if you have different classes and some of them may be more important than others, or if you look at the confusion matrix and you rate your false positives, for example, more important than the false negatives or other way around, these are all things that cannot be handled within the MCC score. So if we want to have this, we also need to choose another metric. And generally, you saw the formula earlier, it's just not that straightforward to interpret. So accuracy and balanced accuracy are very easy to interpret. You can get the intuition quite fast, but MCC is just a bit tricky and hard to interpret. So generally, we hope with these small examples, we show to you that there's not the only one metric that suits all of the different needs for different problems. So we always have to think about what are the limitations of the metrics. Can I now use this metric in the settings? What are the things that I need to consider? And to put all of this together, this is why we have our recommendation framework, and we have a decision tree based on all the different things that we just discussed earlier. So you don't have to look at this in detail, but just to highlight a few things. So for example, we talked about MCC having problem with unequal importance of classes. So we have a question for this in this decision tree. If we have an unequal importance, we probably shouldn't use MCC. Also, if we need to have different penalizations for class confusions like false positives and false negatives, there are also metrics that can compensate for this, while others cannot do this. Or the general class imbalance problem that we talked about is also handled in some of the metrics, while not in the others. So with this diagram, we're capturing all of those different properties, all of those different things in something that we call problem fingerprint. We will talk about this later again, to handle all the different pitfalls of the metrics and making sure that we're guiding the user to the best metric that we can possibly guide them. However, we will still at some point have these notes where we say select from 2 or more metrics, because this decision is a bit too complex and we want to give the final decision for the metric to the user. And for this, we are giving also a decision guide, which tells us the different pros and cons, so the trade-offs when you choose a particular metric, so that you can really decide for your own specific needs, what is the metric in this case that I should pick. Perhaps it's not that important to you that VA is insensitive to predicted values. So then go ahead, please use this. Or for MCC, it's not that important to you that it's harder to interpret. So it always depends on what you want to show.
Looks great. Okay, so, sorry. Yeah, so back to my example. Does this mean that I'm done now when I use this decision tree?
Actually not, as you see in the slide over here. Because these metrics that we showed you earlier only cover one specific part, one specific type of properties that can be assessed. So we call this multi-class counting metrics, because they all cover all of those classes that are present in the same metric score. But perhaps we want to measure different properties. Perhaps we want to have a look at the per class performance. Perhaps one class is more important than the others, and we want to know specifically the performance on this class, or we want to know whether our algorithm is better at one class compared to another class. For this, we could use so-called per class counting metrics, for example, the F-beta score or the positive likelihood ratio. So, and for this type of metric family, we would again have another decision tree helping the user answering the different questions of the fingerprint, all of those covering all of the pitfalls that are important. However, the 2 first metric families rely on that we choose a decision rule on our model output. So we have these predicted class scores from our model, typically numbers between 0 and 1, and we somehow need to decide how we do it, decision cutoff, how do we actually define our confusion matrix. And if we choose a different threshold, then we would also get a different confusion metric, basically also a different metric value. So if we don't want to have this and want to cover those different thresholds, we can use a so-called multi-threshold metrics, things like the area under the ROC curve. Again, we would have another decision tree for this. If we want to interpret our model outputs, then we should use a calibration metric, or we could have very specific application types of metrics. So perhaps your clinicians have a very specific goal in mind, and you cannot achieve this with the technical measures, but they define a metric that you can use. So you should also definitely cover this one. Or you should select a non-reference based metrics, something that is not comparing your predicted image to the reference image, something like the runtime, the memory consumptions, the carbon footprint. So generally, we want to have a comprehensive assessment of our algorithm, assessing all the different properties. And if we only choose one metric, then we won't achieve this. So this is why we are proposing having different metrics for different perspectives.
Okay, so I hope that with this initial example, we convinced you all that there's really a demand for a structured and systematic guidance of users to an adequate set of validation metrics. And if we zoom out now a little bit more, I mean, now we talked about this image level classification, but actually there are different scales of classification. You could also classify at an object level, so in object detection or instant segmentation, or at a pixel level, so for semantic segmentation. And also in the biomedical domain, we have very diverse tasks and problems, right? From the different domains, going from radiological images to microscopy or endoscopic images. So actually, this is the scope, right, that needs to be looked at when you want to address validation metrics in biomedical domain as a whole. And so actually, this is exactly the scope that we used, or that was our ambition to tackle with the Metrics Reloaded framework. And so, as Lena mentioned in the introduction, we worked together here with more than 70 experts internationally for more than 2.5 years. And we had workshops and expert group meetings and lots of rounds of votings to finally agree on the final consensus that is now in our framework. And yeah, to give you a more conceptual overview, I mean, Annika already explained this for our example, but here, maybe a more general view. So the ambition is that we really map from each personalized or custom problem to a set of adequate metrics. And how do we capture all this diversity of different problems? By the first step that we call fingerprinting. So we have a list of questions that are relevant, and they extract, so to say, the relevant characteristics of each problem. And so these extracted characteristics is what we call the fingerprint. And then this is a structure that kind of generalizes across problems. And so based on this fingerprint, then we apply our metric selection process. So these are the decision trees that Annika showed, where then the questions that guide you through the tree are answered by your fingerprint answers, so to say. So using your fingerprint, you get to your set of adequate metrics. And what's also happening in the fingerprinting is that the problem gets mapped to one of the 4 problem categories. So image level classification, object detection, instance segmentation, or semantic segmentation. And yes, so based on this problem category and your fingerprint, you get mapped to the final output, which is, as you saw, the final node of these trees is our different metric candidates and also decision guides if it gets too complex. And you need to kind of make your own decision and weigh different factors by yourself. And so that's the general concept. And to get a bit more technical overview, this is kind of the meta view of our framework. So you see on the left, the small box, this is the fingerprinting and the problem category mapping. And then the big box in the middle is the metric selection. So here you already saw the blue trajectory. This is what Annika showed with all these little different sub-processes. So each of these is their own decision tree where you kind of collect metrics along the way. And you can see now the other colors, purple, green, and yellow. These are the other problem categories. And first of all, you see that there's substantial overlap between them. So going through the same sub-processes. So this is a great assurance for us that it's totally makes sense to address all of these categories at the same time, right? And not have like separate metric recommendation frameworks for each of these categories. But you also see that in contrast to this blue trajectory, now additional stuff has to be considered for other categories. For example, on object level, so the purple and green arrow, you see that you also need to select a localization criterion, because in these tasks, you need to localize your objects and also need to think about how you match them with the reference objects then in S9. And for semantic segmentation, we have different metric families, like, for example, the overlap-based metrics, like the die-score, or more boundary-based metrics like the Hausdorff distance. And finally, we also give some guidance about metric application. So this is the box on the right, where we talk about how to reliably choose your decision threshold, for instance, on your continuous output scores, where we see a lot of pitfalls happening in practice at the moment, but also give some guidance on how to aggregate metrics across classes and different metrics, and how to rank models properly, and also how to adequately report your final results. And so one last thing that I want to mention is that we're not kind of leaving the user alone with the statement, okay, you should use the MCC, but we also provide information about the metrics themselves. So we have an extensive library of all the metrics in our pool, so to say. And in these cheat sheets, or we give a structured, dense and concise information with hands-on pitfalls and recommendations, but also references in literature for each metric. And we also provide software implementations that are kind of standardized and reliable for all the metrics. And this is implemented in our GitHub repo that's part of the MONAI project, where you can find these metric implementations.
Also, we wanted to give recommendations for common biomedical use cases. And for this, we asked the community via Twitter and also the consortium, what are the use cases for which you want to see recommendations? And based on this, we compiled a list. Here you see the examples for image level classification, where we hope that most of the people find their own specific use cases and can follow our recommendations, because we also give the fingerprints so that they can easily follow, okay, which decisions were made, and perhaps for their own specific problems, they have some different fingerprints so that the recommendation would change. But generally, based on our literature research, based on consulting experts, these are the recommendations from our system that we would give to you. Also, you saw that this framework is not straightforward, so it's a bit complex. And also what many people suggested is that it would be good to have an online tool. And this is also what we are working on. So here you see the first beta version of this framework, just making it easier to follow. It gives you instructions where you need them. If you don't need them, you can just scroll through them. Ignoring all the complex stuff that you perhaps don't need, just having it in a big more condensed fashion, and it makes it a bit easier so that you don't have to scroll through our, to be honest, very long paper. And here you get all the information that you need at this time point. So we also consulted some designers to make it look a bit more nicely, but currently I think it's already a very good thing to have, and we hope that many researchers in this way also use this system. So let's go back to this overview. And this is also now the end of our talk. So we saw earlier that we have different metric families that we are concerned with. And for the image level classification branch, I briefly talked about calibration metrics. So we would somehow want to make our model outputs interpretable. And this is something that we found during the process of working on this framework. People really wanted to have this decision tree specifically on calibration metrics, because this is something that is not really popular in the community, and we really wanted to make a step forward. And for this, I'm very happy that we have Florian here today, who will give the next talk on calibration, and we hope that you also get some guidance over there with this talk. Yeah, and then I would like to thank you for your attention. We're happy to answer any questions, but I think now we would first go on to Florian and get the questions afterwards. So yeah, thanks a lot for your attention.
All right. Annika, you already covered almost all my introduction, but I'm very excited to have Florian here. Florian did his PhD in physics and then spent several years as a postdoc and PI at the Helmholtz Center for Environmental Health, Munich, and the European Bioinformatics Institute, Cambridge. He then worked as a guest scientist at the Helmholtz Center in Munich, and also had an appointment as senior scientist for industrial AI and probabilistic machine learning at Siemens. The recent news is that he just earned a ERC Consolidator grant on trustworthy AI. Congratulations this round. A very well-fitting topic today. And we recruited him to Metrics Reloaded because there was such an urgent need apparently from you as a community to have recommendations on metrics. Some of you may remember that we did a little crowdsourcing social media campaign, and this is what came back a lot from the surveys, not to just focus on discrimination, but also on calibration. So we also took that challenge and recruited some calibration experts aboard, and one of them is Florian, who was actually leading this initiative. He has a recent NeurIPS paper also on the topic. And yeah, Florian, it's great to have you here, and the stage is yours.
Thank you very much for that kind introduction. So I shall dive right in, and we'll speak a little bit about the reliable estimation of uncertainty calibration, its challenges, and maybe some recommendations we converged to within the consortium. But before I really get into the details, I'd just like to start maybe with a motivating example. So in case you're not so familiar with calibration, maybe this will convince you that it's something worth thinking about sometimes. So let's assume we have like the task to classify skin lesion images like this one into whether it's a benign lesion in nevus or whether it's a malignant lesion, skin cancer. And let's assume we have a model that is trained to an accuracy of 90% on some independent test set. And then it makes a prediction on this particular sample during deployment, and it will say, this is a benign lesion and I'm 99.8% certain. That would be good, right? So you would trust that prediction, I guess. But then when you zoom into this image, the model would say, well, actually it's a melanoma and I'm 93% certain. So the model makes an overconfident prediction that is actually false. And the problem is not so much that it makes a false prediction because it has never seen these images during training. The problem is that it makes it with such an overconfidence. So for us to trust the model, what we'd like is something that is calibrated in terms of confidence scores. So we can't improve accuracy, but we'd like for the confidence score to have a better quality. And if the accuracy in this case is around 50%, maybe a good confidence score would be 53%. And when we talk about calibration and calibration errors, we would like for this confidence score to match the accuracy for all levels of confidence scores. In other words, the empirical success rate of the confidence scores should match the empirical success rate of the associated predictions, that way around. Because then when you have these calibrated and reliable confidence scores at the level of these individual predictions, we can have like many new downstream applications opening up in this research field. Okay, but before we do that, we sort of somehow have to formalize uncertainty quantification. We somehow need to have like a good framework, formal framework, on how to quantify how good and reliable the quality of the confidence scores are. And one way to do that is to say that predicted class scores or confidence scores should represent the true likelihood of events. That's still a little bit vague, maybe. And in practice, actually, there exist different types of calibration, in particular, 3 different types. And the strongest and most general form of calibration is called canonical calibration. And here, canonical calibration says that the probability of a model's output score belonging to some certain class should always match the predicted confidence score. And I think that can be nicely seen in this formula where we have like our model output f of x. So this would be the confidence score of our model. And this should match this term here, which is the conditional distribution of our target y given f of x. So here we condition on the output of our classifier, and we want the model output to equal this conditional distribution. All right, so to make it a bit more tangible, I have here the example from the Metrics Reloaded paper. What we have on the left-hand side is 6 different predictions, model outputs, f of x. We have a 3-class problem, so we get 3 different confidence scores, 1 for each class. And on the right-hand side, we have this conditional distribution of our target y given f of x. And what we want is for these model outputs to match this conditional distribution for all the model outputs. And we can compute that by just using some kind of distance function. It could be like the squared error, it could be the L1 error, or like anything. And what you can see at the first glance is that, okay, these rows are not equal, so the calibration error, the canonical calibration error will be greater than 0, actually. Okay, good. Hope this is like, the idea is roughly clear. So I've said there's 3 different types of calibration, and this was canonical calibration, the strongest form of calibration. Another form of calibration would be class-wise calibration, where you say, well, actually, I'm interested in specific classes, how well a model is calibrated for each of the classes I am predicting. And here we only look at marginal distributions. So only the marginal distributions need to match. So we introduce a new index k here. So this is the model output of the kth class, and this should match the conditional distribution, or when I condition on fk again. And this is again, as I said, a weaker form of calibration than a canonical calibration. And this is something we can also see here at this example. So we still have our same 6 predictions, and now we focus on class 1. So we look at the first column here. And we want for each f of x, or each model output, for it to match this conditional. We now have 3 unique model outputs, 0.1, 0.3, 0.6. So for 0.1, we look at this term here where we condition on f of x, which would be 0.1. So we have like these two instances here. So we take the average of these two, which would be 0.1. And we see, 0.1 matches 0.1. So no error here. Same thing here. They perfectly match at 0.3 and they match at 0.6. So in this example, actually the class-wise calibration error for class 1 would be 0. And the example is constructed in a way that this is also true for class 2 and class 3. So when we then take the average of the three classes, we have a class-wise calibration error of 0 in this case, which illustrates the weaker form of calibration that this class-wise calibration error is. The third way of looking at calibration is top label calibration. So what we do here is we consider only the top label for each prediction. So top label sort of means just the most likely class that our model predicts of being the actual class. And if we want to write that in a formula, we can introduce a new index capital K, and capital K is the argmax over all classes. So it's really just the most likely the class that our model predicts. And this should match then the conditional distribution where we condition on this F capital K. And this is the weakest form of calibration, which I can show you here again from the metrics reloaded example that we constructed. So now what we do is we only look at the most likely confidence score. And in all these examples, it's 0.6. So we only have like one f of x being 0.6. We condition on this 0.6. And so we have to take the average across all of these values. And we'll see, okay, this is also 0.6. So f of x always matches this conditional, basically, because we only have one value here. So top level calibration in this example would also be 0. And yeah, as you can intuitively see, hopefully this is even weaker than the class-wise calibration error that I've just shown you in the slide before. Okay, so that was a little bit abstract in terms of what kind of calibration errors exist. But in practice, as a practitioner, I would like to really, well, I need to compute it and I want to put a number on it. And so I have to have a few more choices to make on how to do that. First of all, I need to decide on a distance function between f of x and the three conditions. So I said, you can compute any kind of distance, but actually what's most commonly used are L1 and L2 errors. But people have also looked at other distance functions, for example, based on kernels, or like a generalization of the L2 calibration error to the LP calibration error is also something that you will commonly find in the literature. Okay, that seems quite straightforward, but there is a big but, and namely that this conditional distribution P of y conditional f on f of x is unknown. And all we can do is we can estimate it as an expected value. So, for example, in the beginning, I said, okay, if we have like predictions with a confidence score of 0.8, I want that all real cases with this confidence score should have an accuracy of 80%. And so this 80% would be my expected value, right? But the problem now is that, well, actually, I have a continuous output, right? So I probably in practice will only have like one prediction with an output of exactly 0.800000. So based on one sample, I will not be able to estimate a reliable expected value, right? And this is the whole dilemma of these canonical calibration estimation problems, that this quantity is unknown, but I only have like one sample per prediction to estimate it. So I need to come up with some kind of workaround. And a very simple workaround is spinning, that I say, okay, now I don't only look at like my each point in my distribution of my output model f of x, but I bin it and I look at all predictions between 80 and 90% together. And if I look at all predictions with a confidence score between 80 and 90%, well, I have a decent number of samples in my validation set that I can use to compute this expected value, or aka the accuracy. But I don't have to use binning. I can also use other ways. For example, kernel density estimators have been shown to also work quite nicely and even more robust than these binning estimators. Okay, so taken together, that means in practice, we have 3 choices to make when you want to compute a calibration error. First, we need to decide what calibration type is sort of most relevant for us, canonical, class-wise, top label. Then what distance function do you want to use, L1, L2? And finally, what estimator do we want to use, spinning or KDE, or maybe something different even. So here's an example on how that works for a specific combination that is, I guess, the most widely used one. And that is the combination of top label calibration as the family of calibration errors, the L1 norm as distance function, and binning as the way of estimating the calibration error as an estimator. And so this is visualized here, where basically we have, like in this case, 1, 2, 3, 4, 5 bins, and we group all predictions with a confidence score of 0.8 and 1 together in this bin, for example, and then we can compare this empirical value. So we know, okay, this is our confidence score, which is on the diagonal, and then we would like to match this to the average accuracy, which would be like the estimation of the conditional distribution when we condition on our confidence scores being between 0.1 and 0.8 and 1. I don't know what I'm talking about. So in other words, what we want is for this bar to be up here. We want for all predictions with a confidence score between 80% and 100% to have an accuracy that matches that. So it would be here at 90%. And you can see here, this is not the case, because we have like this big gap here, and all predictions with this type of confidence score only have an accuracy of sort of 80%. So they're overconfident, and you can see the same thing here. So we always have like this gap on the bottom. And the ECE then basically says, okay, I just take the average of these gaps and I weigh them by the number of samples in each bin. So the ECE is just then the weighted average of these red rectangulars, which are like the gaps, or the L1 norm between accuracy and confidence score in each bin. And that would be like this expected calibration error. All right. Okay, that seems fairly straightforward to compute, right? And also like a useful and interpretable quantity. But there are some limitations and caveats that come with that. And there are also some alternatives that I'd like to briefly cover in this slide. So the biggest limitation, I guess, in these with estimators like this one are that most of them are biased. And biased in that context means that the estimated error depends highly on the number of samples that I have in my validation set. So I have a model that is fixed, so it has some kind of true unknown calibration error. But if I use the ECE with the spinning scheme, the value I get and that I compute via the spinning scheme really depends on the number of samples in my validation set. For example, what we did here is we simulated a model with a perfect calibration, which is the blue curve here. And then, so we know the ECE should be 0 because this is how we simulated the model. And then we just drew 100 samples, 1,000 samples, 10,000 samples from a validation set and computed the ECE via the binning scheme. And if we did that for 100 samples only, the ECE, as described in the previous slide, would get a value of 7.5%. So it would suggest that the model is actually quite miscalibrated. And only if you have enough samples, the ECE approaches the true calibration error of 0. So and this is what I mean by bias. It really just depends on the number of data points I use to evaluate my my metric. That can make all the difference here. So this is something to be really be aware of. Another challenge or caveat is that some distance functions are harder to interpret. So we just now use the L1 distance, but 2 distance is also very simple to interpret, right? It's just squared difference or the absolute difference. But there are other methods that are based on kernels where it's much harder to interpret what these actual numbers that I get really mean. They do have some advantages, as in that they don't have the problem of this bias. So they can also be a very good choice in some circumstances. An alternative would be proper scoring rules. Proper scoring rules measure not only calibration, but they really measure the overall performance of a model where they combine calibration and discrimination. And examples would be the negative log likelihood or the Breyer score. And one interesting property is that these proper scores can be decomposed into separate terms for calibration, sharpness, and sometimes generalized entropy. Okay, now that we've covered sort of like some more abstract basis or theoretical basis, and we know how to quantify these errors, I'd like to talk about a couple of use cases briefly. And so one very common use case is model recalibration. And this is one of 4 use cases that we identified in the metrics reloading consortium. And here you have a classifier here, and you would like to look at maybe a few different recalibration methods. So you want to transform your classifier outputs to improve the quality of the calibration. Your accuracy shouldn't change normally, but you just want the quality of the confidence scores to be better. And then you would select sort of the best one. And this is, for example, the most common way of doing that is temperature scaling. And there you learn a single parameter, T, a temperature. You take the logits of your neural network, if you assume you use a neural network, and then you have these transform logits, then you need to renormalize via a softmax function. So this is robust, but actually not very expressive. There are also other alternatives. For example, you can use a prediction-specific temperature. So you don't have a single parameter, but the parameter depends on your individual prediction. And this is, for example, something we looked into last year and called this PTS, parameterized temperature scaling. And what we did in this plot is like exactly use case 1. So we sort of have one classifier, and we compared many different ways of doing our recalibration. And for example, ours is here. And then in this case, we use the ECE to look at which of these recalibration methods works best. And then we would retain this classifier with the lowest ECE. But actually, what we did there wasn't very clever at all, because the ECE is not such a great metric to use when we make this comparison in use case 1, which is also something that we converged to within the metrics reloaded consortium. I'm going to show you next why that is and how we can do this better. So I've mentioned before that there are these proper scoring rules, like or proper scores like the Breyer score, and they can be decomposed into a sharpness and a calibration term. And it turns out that quite nicely, this calibration term in the decomposition is equal to the L2 canonical calibration error that I've introduced at the beginning. And another nice thing about the Breyer score is that there is a very simple unbiased estimator that doesn't depend on the dataset size, that it just can compute via the mean squared error. So that means if I have an accuracy preserving recalibration, I can just compute like the root Breyer score and take the difference, and that will give me like a very robust estimate of the ground truth of calibration gain. And this allows me to analyze really the reliability of common estimators of canonical calibration for this use case 1, like for the ECE and class-wise calibration and so on and so forth. Because I know what the ground truth is, right? So in a recent NERSC paper, we looked into that. We trained like neural networks on different data sets and applied different types of accuracy preserving recalibration methods. And what you can see here is the calibration improvement for different calibration estimators, like the ECE is like the orange one, if you want to focus on that maybe. And we looked at that for different test set sizes. And you can see in red, sort of the ground truth that we can compute via the Breyer score, which is the flat line. They shouldn't depend on dataset size, but you can see that all the other estimators really heavily depend on dataset size. And some of them say at the beginning, oh, actually, your model gets worse after recalibration with a negative calibration improvement. And then only when you get to like large sample sizes, they say, oh no, it gets better, but they overestimate calibration gain. So they're really, really dataset dependent, dataset size dependent. And the same is also true for other datasets. We looked at CIFAR10, and you can see really this going from, oh, there's no calibration gain, to saying, oh no, there is one. That's too high. And in this case, for example, the ECE really overestimates the calibration gain that we would get. And yeah, the same thing for ImageNet. And here, this overestimation of the calibration gain by the ECE is even more prevalent. So yeah, as I said, with the knowledge that we have now, I definitely wouldn't have used the ECE to compare the recalibration performance of different recalibrators, but I would have used something like this, this method here, like the RBS or an unbiased estimator of canonical calibration. So there are more use cases, not only like the comparison of recalibration methods for one classifier, but you can also look at multiple classifiers here. Or you can say, I want to have a ranking not based on calibration only, like in these cases, but also based on discrimination. In addition, in the consortium, we identified a fourth use case, which is understanding the reliability of predicted class scores for better interpretation and communication. And so I'd like to say a few words to this use case as well before I wrap up. So here for this use case, we want to understand the reliability of class scores. And one downstream application could be use case in silico stratification. And here, for example, I could have a use case like in the skin lesion classification where I say, okay, I have a model where I trust predictions with a confidence score that is greater than some threshold. But otherwise, I will refer it to an expert. And if I want to do that, I need to be sure that my class scores are reliable. And they have to be reliable really throughout the life cycle of the model. And what we've seen, and others have observed as well, is that modern neural network in particular make systematically overconfident predictions under domain drift. So if there's a model trained on MNIST data, like here in SIG, and you distort it and feed it with something that it has never seen before, it will make wrong predictions with a very high confidence. For example, here we have a distorted 6 that is not anything, and the model will say, this is a 2 and I'm 100% certain. And the same holds for the skin lesion classification task. So if we train a model based on images taken in Barcelona and we deploy it in Sydney, then we would get wrong predictions with a super high confidence score. And this is really something where calibration error helps us to quantify what's going on. And in particular, we need to have reliable confidence scores really for in-domain settings, but also for completely out of domain settings where we maybe get a faulty image. So the sort of synthetic example would be MNIST, trained on MNIST and tested on fashion MNIST, for example. We had some simple idea on how to make that better, where you can just generate a perturbed validation set before you do post-hoc calibration. And then this is just like to illustrate this use case a bit further. Because, for example, when you do that, you can really improve the reliability of your confidence scores. But what's also really important is it does not increase accuracy, right? So this is an example where we have like, I think it was ImageNet, and we have like increased perturbations. At 5, the model sees images that never seen before. So in whatever you do, whatever of these many calibration methods you use, the accuracy will always go down, and this will not change anything. So when we look at calibration, we always have to keep in mind it's really model dependent and conditioning on the classifier here. But in terms of ECE, so the quality of the confidence scores, we can do something. So for example, like our approach is always the dark one, and then you can see, okay, even if we have like a really high perturbation, we can like sort of cap the ECE at between 5 and 10%. So that means the calibration error really can communicate sort of a reliability interval in our confidence scores and tell us, okay, I have a confidence score, and this confidence score of 80% will be reliable up to 5%. And this will then allow us to decide, okay, can I use my model now for downstream applications like in silico stratification or not? Or do I need to improve it any further? Or do I just have to stick to my expert classifier, so to say? Right. So, okay, I'm going to wrap up now with like just very brief recommendations in a nutshell that we came up for these different use cases. But I'm not going to go into too much detail. So for the use case 1 of the recalibration that I gave in the beginning as well, what we want to do is we want to have a proper scoring rule like the Breyer score or an unbiased estimator of the canonical calibration error. If we have multiple classifiers, we either report the class-wise calibration if we have unequal interest in classes, or we recommend reporting the canonical calibration error. And for overall performance, for sure, we will want to report a proper scoring rule. And for the 4th use case that I just went into detail, it's maybe a bit more complicated, and there really depends on the individual application. But there's help. So there's also like this nice tree that will guide you through into which of the many different calibration errors you will actually use. In general, maybe as a last comment, ECE is usually not a great choice, except if the focus is on the decision-making process, like in my last example, when I have this in silico stratification, then the ECE really mirrors that process. All right, with that, I'd like to conclude and maybe summarize that, okay, calibration error is a model-specific metric to measure the reliability of the confidence scores, but it always needs to be used together with a metric that also measures discrimination. There exist many different flavors of calibration errors. You have to choose according to your own use case, maybe using the nice decision tree, and beware of the limitations. Oh, and really what's also very important is this field is moving rather quickly, and so I would recommend to always look out for the latest unbiased estimator of maybe interpretable canonical calibration. This is probably a good choice. And with that, maybe just like to thank my students and collaborators, and thank you for listening.
Thank you so much, Florian. I wish I had listened to your talk before reading about calibration first. I think that was very helpful for me personally. Yeah, when I looked at your slide, I realized that I forgot to mention your last station of the academic career, which is obviously important. So I want to take the opportunity to mention that you're now a professor at the University of Frankfurt and also at the German Cancer Research Center and the German Cancer Consortium, DKTK. Yeah, so sorry about that. And yeah, thank you so much again. And I would say now we move on to the questions. Camilla, do you want to take that?
Yes, thank you, Lena. So thank you so much to the speakers. I think both talks were very, very clear. But fortunately, we have a few questions. So I will just start with the first one. Are there any recommendations on data sets that provide both algorithms, segmentations, and ground truth, such that one could explore the performance of the different validation operators? I think this question is for Annika and Paul, because it was posed quite early in the webinar.
I mean, sure, you could, I guess, use, for example, NNUNet. There's all the pre-trained weights are online, and you can run them on the medical segmentation decathlon datasets, which are also public. And you would easily get then the predictions for these 10 datasets and could explore some different metrics. I think what's important to say is that with these empirical studies, you only get so far, right? You have then, for your cases, you have 3-4 different metrics that you can look at. But you can't then really say this is correct or this is incorrect. Sometimes it's not that easy, right? In our experience, it really always depends on the domain interest. So you have done more like an answer like, okay, if I'm more interested in this, then this metric reflects it better. Or if clinically this is more relevant, then I should use this metric and so on. So that's why our framework is always rooted, so to say, in the interest of the user, rather than saying this metric is empirically better overall.
Great, thank you. I think, Annika, would you like to add something, or just that already?
I think this already pitches it quite good. So it's always important to have the domain interest. It always depends on your research question, what you want to show. But I think NNUNet, for example, is a good idea to start with.
Okay, great. Then the second question is, there are clearly many different metrics available, and I think the decision charts are great. Do you think there is any place for developing new metrics, or are the existing ones sufficient?
I think this goes well with what Florian said in the last slide, especially in calibration. There are so many different metrics popping up. So it's also for us, it was not easy to design this flowchart. So I think with our framework, we had a good overview of the existing metrics. So we had a look at the popular ones, but we also integrated metrics that we were not aware of beforehand because other people suggested it to us. So yes, I think there's definitely room. And also this is something that we hope to easily do with the toolkit. So if we come across with different new metrics, new recommendations, that we can easily insert it there.
Yeah, I agree. So I think it's a bit counterintuitive, but it's really a dynamic field. So if you look at the pool of metrics that we have, I think a large part of them has been proposed in recent years, and not only calibration, but also in segmentation, you have the normal surface distance or normal surface dice, for example, or in object detection and instant segmentation. I think there's also great room for new metrics. For example, we also have a MICCAI publication or submission on the way where we propose a metric for size-aware object detection. So I think it's actually a kind of vibrant research field, despite what you would think.
Okay, wonderful. So I suppose users can expect that these new metrics are also, that the framework is also updated with all of these new metrics that are coming out.
Yeah, and maybe just to, since this is a panelist session here, maybe we could even have something like a blackboard for people, like, you know, in the online tool, a blackboard for people to say, yeah, well, sorry, but none of the metrics works for me. I need one. And then maybe this could, you know, trigger some new research. We could consider this.
Wonderful. Then I will move on to the next question. So thank you for the insight into this important framework. For the use case of image level classification, there are models for image level classification on video, for instance, on endoscopic surgery. The metrics reloaded framework focuses on frame-wise validation metrics. What do you think of F1 at K as a metric to assess video segments rather than the frames separately in order to penalize over-segmentation? Could this be used true, or would you refrain from considering it?
I'm not an expert in video segmentation. It's true that we don't cover this at the moment. So I think if you think about these overlap-based metrics, when we have images in a data set, we want to kind of compute it per image and not per data set in the biomedical domain, right? Because we don't want large structures of one patient to overshadow small structures in the next patient. But I think in video it's different. You can make, I guess, assumptions about the smoothness across the temporal dimension. And it might be a better option here than for images in a data set. But Lena, as a Kami or a person, maybe has more insights into this metric.
Yeah, maybe actually, Raya, maybe you send us an email, because interestingly, we will have a workshop exactly on endoscopic vision metrics. So the next step is to go from frames to videos. And we will actually tackle those problems. So there will be a workshop at SAGES in Montreal on March 27th, I think it is. So if you're interested in this topic, just maybe send me an email pragmatically, and then we can go from there. And to the whole community, the same holds for you, and hopefully we will come up with some recommendations also for endoscopic vision and video analysis in general.
Okay, I think the answer can't get better than that. So I will move on. I think this next question is for Florian. Do you know which direction the SS estimator is biased to? Does it prefer under or overconfident models?
That is a really excellent question. We haven't looked into that in specifically, so I actually don't know. But yeah, I'm curious to see that. It's maybe something really should get started on.
Okay, great. And the next question is also closely related to that. When studying the standard SS estimator as function of dataset size, do you only use equal width binning, or do you also study the equal count binning, the 8AA variant?
Yeah, we sort of empirically, we only studied equal width binning, but we also have a theoretical analysis on how the ECE behaves with dataset size, and that also holds for equal count binning. So the general shape that you saw in that simulation, that will also be true for the equal count binning.
Okay, wonderful. I think there is one question here which is quite relevant, which is about the URLs. So basically all of the links of all of the materials, everything. I mean, I would say you could post this in the chat, but maybe a better option would be that these are posted in the Twitter. Let me just share all of the social media channels so that people can find.
Yeah, so we could probably provide the link to the paper, and also the metrics loaded paper, which also contains the link to the tool, and then also explicitly the link to the tool. For that, you need a password, but we basically give it upon request. So Annika, maybe should we just paste it in the chat here?
Yeah, just did it. But if you also want to have a look at the paper, there we have this link, also the link for the GitHub for the MONAI repository, where we implemented all the metrics. So I think you have all of this together. And also something that someone asked, perhaps we could also mention this from the panel. this recording will also be available on YouTube. So if you missed something, if you came later or had to leave early, then you can also watch everything later.
Exactly. You can see here, if you go to YouTube to the channel of the MICCAI Educational Initiative, you will find also the previous webinars of this series. We will upload this one probably in the next few days. Yeah, and here you can also find our other social media channels from MICCAI students, from via special interest group. Also somebody asked about joining the Slack workspace for MICCAI students. I also posted the link there. You can find this in the Q&A.
And also, if there's topics that you would like us to cover in this webinar series, we're very open for suggestions and also speakers, whatever is interesting for the community.
Okay, there is one more question. Maybe if you still have a few minutes, we can answer that. How do you validate your validation operators? Who watches the watchman? Or another way to say this, how do you ensure that your validation operators are well calibrated? How do you ensure one is not committing the fallacy of assuming the consequent? So basically, this validation operator shows good performance for my algorithm, therefore it must be a good operator.
Yeah, I think this goes in the direction of what we said a little bit before, right? And so there is no real ground truth, right? Where you can say this metric is correct or incorrect in a certain way. They can only sort of measure different properties or characteristics of a problem from different angles, right? And it's kind of on the user to decide what is the relevant or important angle. And as for inherent flaws in metrics, I think there's literature out there, for example, for weighted cones kappa, which is heavily used. There's some simulation studies that show weird behavior in certain application scenarios. And so it's possible, of course, to investigate these metrics and look at pitfalls, right? So we have an extra paper actually only covering all these pitfalls of the metrics in certain scenarios, which you can do with simulating little toy experiments or just thinking about it on a conceptual basis, or what the person in the chat suggested, to just empirically play around with these metrics. You can do that. In the end, when you have sorted out these red flag pitfalls, you will still be sitting with the problem of which metric is the most important based on your personal application, I think.
Yeah, and also this is one reason why we had this large consortium with more than 70 experts, because we cannot know every little pitfall or limitation, and we asked people about the different things where we then compared the different pitfalls, and all of the recommendations are based on this. So we hope to cover most of the things, but of course, as Paul said, there's not a ground truth for this.
But so to say, we were also thinking about this, right? When we submit our paper, and I mean, reviews, they want to see kind of always a proof that something is correct. And that's a bit of a funny situation for us, because you cannot prove that your recommendations are correct. So sort of all we can do is say, and that's by definition, right? Not because we were lazy. By definition, we can only say, this is kind of what the community as a whole agreed on is sort of like useful guidance, right? And as Annika mentioned, we're not imposing anything here, but we're being very careful also about the way we phrase things in order to reflect the ambiguity or the complexity of these decisions.
So maybe the last question is actually also relevant. Are the calibration methods also implemented in MONAI?
Yes.
And there's a personal disclaimer of Tassos, who has actually worked on this problem, reliability and validation of medical images, and would be keen to have a discussion. We're always open for discussion, I think. So just send us an email. Okay, so Camilla, do you want to do the closing?
Yeah, so thank you everybody for coming. Thank you to the speakers. Those were really interesting talks. I think they have been added to all of the material that's available to the community when they want to select appropriate metrics. Thanks for the talks. Okay, I thought there was another question. So yeah, thank you everybody for joining. We had over 140 attendees, and thank you to the panelists. And we will see you on the next edition of this webinar series.
Thank you.
Bye, everyone.
Bye.
Thanks for having us.
Bye-bye.